I'm Tim Felgentreff. I am part of the GraalVM Python team in Oracle Labs. But this talk isn't going to be about Python. It's going to be about how especially the native image capabilities of GraalVM enable you to do cross-platform development on top of GraalVM. And I'm just going to talk about how that enables that and how it's faster also on different platforms. A couple of you have probably already seen this slide, but just in case you haven't, GraalVM team is a big team. I'm just one person in that team. While I tried to make everything in these slides truthful and to the best of my knowledge, I might have made mistakes or plans may change, so please don't take these slides as a plan to productize anything in particular. Is that out of the way? GraalVM. So there's different ways to look at cross-platform development on GraalVM. And this is one of the pictures that we always use to kind of explain what GraalVM is to different people. Because it kind of shows the different orthogonal points of view that you can take when you're talking about cross-platform on Graal. Because GraalVM already is a platform, right, that allows you to run allows you to run different languages on top of it. Obviously, the JVM languages, Java, Kotlin, Scala, what have you. But also dynamic languages. Right now, we officially have JavaScript and experimental languages like Ruby, R, and Python. But GraalVM also allows you to run statically compiled languages like C, C++, and Rust that compile to LLVM bitcode. And for all of these, GraalVM is the platform. So all of these, so everything I'm going to say here in this talk pretty much applies to all of these languages that run on top of GraalVM. Then GraalVM itself runs on different platforms. The common thing that people thought about and that kind of where historically GraalVM started is running on top of Hotspot, either an OpenAge JDK or an Oracle JDK. And thus, it's cross-platform in the sense that the JVM is cross-platform. And in this configuration, if you're running on OpenJDK, basically what you're getting is kind of the same thing as if you were running on top of Hotspot with those capabilities, just with GraalVM and Graal, the Graal compiler is the just-in-time compiler, and these capabilities to run different languages in a high-performance manner. However, the GraalVM also comes with a feature called native image, and that allows us to embed it into different other platforms. One prominent one that is already included in GraalVM right now is on top of the Node.js platform, which is basically a huge bunch of C++ code, right? And you're embedding some JavaScript runtime into that huge bunch of C++ code. GraalVM also runs inside the database, the Oracle database or MySQL, for example. And with GraalVM native image, you can also compile anything, any Java application and any of these dynamic language interpreters or the LLVM bitcode interpreter into a standalone binary. The technology that enables all of these things really at the core is the Graal compiler. This is really where the project started, if you will. The Graal compiler started as a research project to write a just-in-time compiler, a production just-in-time compiler in Java, so in a higher level language than is common for just-in-time compilers, really. Usually these are written in C or C++, kind of system languages, if you will. It being written in Java had the advantage that we could make it more modular and more easily extensible and maintainable than especially older just-in-time compilers that have been grown over the years and that had kind of outgrown their potential to be extended, including just-in-time compilers for Hotspot. GraalVM and the compiler inside comes in two different flavors, the Community Edition and the Enterprise Edition. I'm not going to get into it too much in this talk, just so much here in the context of the Graal compiler. The community edition has fewer of these modular optimizations that we're able to plug into the compiler. Enterprise gives you more optimizations. That's just in the context of a compiler. There's other advantages to Enterprise that aren't relevant to this talk. And some of the advanced optimizations that are in the Graal compiler that are relevant for the performance that GraalVM gives you are partial escape analysis, where we understand that some objects, for example, never escape from a certain code path, so they don't actually need to be allocated, for example. Path duplication, where we try to specialize code path by duplicating them for your specific workloads, and inlining, very, very sophisticated inlining strategies. And what that allows us to do is easily deal with high-level language concepts, for example, in Java. Like here, where you have this streaming API usage, and where traditionally we had to work, or a lot of work had to be done on a just-in-time compiler to make the above code just as fast as if you had spelled it out in this lower level kind of way. And the Graal compiler, on the Graal compiler, really this on top here really turns into the same machine code as the one here at the bottom. There's really no difference. The Graal compiler sees through all of this abstraction and makes the code go as fast as possible, really. Because these kind of high-level concepts are poorly expressed in more traditional, older sets of JVM benchmarks, we have partnered as the labs with, among others, Charles University in Prague to make this, create a new benchmark suite that is more, that really shows more modern workloads on the JVM. This new benchmark suite is called Renaissance. And it has a few different modern workloads, including the usage of these high-level APIs, like the streaming APIs. There's benchmarks in there that use Scala as an example of a different language on top of the JVM that that, for example, the hotspot JIT compiler had to have a lot of work done to support more efficiently. And here what you can see in this benchmark is there's like all these separate benchmarks, and here at the end, that's what you want to look at, is the geomean speed up over C2 for GraalVM Enterprise Edition and Community Edition. And really what you want to take away from this is that on average for these kind of modern workloads, if you're running Enterprise Edition, you're going to be about 30% faster. And even if you're just using Community Edition, you're already going to be 6 to 7% faster for these modern workloads on average. That's the kind of speed up you can expect. And if you're more interested not only in these high-level APIs, but in different JVM languages like Scala, we can look at the Scala bench also. And here, the Graal compiler really shines. And you can see higher geomean speedups here, up to almost 40% for Enterprise Edition. And these speedups are one of the reasons why Twitter has been using GraalVM and running some of the services on GraalVM for a while. And that also kind of goes to show that it's already quite a stable, it's stable. It's a stable, very stable compiler that you can use that's production ready. Now, it being written, the Graal compiler being written in Java, if you tried it maybe a couple of years back, you may have noticed slower warm-up times compared to the C2 compiler, because the Graal compiler itself being written in Java first had to warm up itself, and then had to be warmed up itself, and then it could warm up your application. And before we get into native image proper, I just wanted to show that we've completely fixed this problem with what we call libgraal, where we use GraalVM native image to produce a shared object of the compiler itself. So it's kind of this meta-circular thing where you're using the compiler itself into a native object, and use that native object to as the just-in-time compiler, for example, on hotspot here. And with libgraal, instead of the Java version of the Graal compiler, you can see that you're warming up extremely fast and you're really on par with C2, and then you're overpassing it for peak performance. So there's really no reason then to not use the Graal compiler and GraalVM instead of Hotspot. And not only is this important for your server workloads where you care about peak performance, it's also important for workloads that take less time and that you're starting over and over again. Like if you're compiling, for example, as a developer on your development machine. Here are some numbers comparing just running the Scala compiler on different projects, normally on OpenJDK, Java 8, on GraalVM Enterprise Edition, and then using Bloop, which is an alternative Scala compilation tool set where you pipeline the compilations, both again on Java and on GraalVM, well, on JDK and on GraalVM. And in each of these cases, you can see that GraalVM, because it warms up quickly now and it reaches high peak performance, actually finishes the workload faster than it would if you're running the compiler without GraalVM. So this is about developer productivity, right? This is not only about using fewer servers to run the same stuff or less CPU time. This is also, think about hundreds of developers waiting an additional couple of seconds every time they're compiling something. And this is also one of the advantages that Graal gives you. So if you're not using GraalVM yet, there's really no reason not to at least give the Community Edition a try, because it just probably gives you a 7% performance boost right from the bat. And you can also try the Enterprise Edition for evaluation and see kind of where you're going to get likely around 30% speed up. So really don't waste the time and also not the energy, the resources. Think about the climate and use GraalVM. Now, I alluded to native image for the Graal compiler for itself, and native image is at the core of this cross-platform story that we have for GraalVM. And just as a very, very kind of abstract overview of what native image does, the goal of native image, GraalVM native image, is to give you fast startup, small footprint with the same nice high peak performance that GraalVM on OpenJDK gives you. And how that works is it takes all of your Java code, so your application code, all the libraries that you're using, the JDK standard library, and some libraries in what we call substrate VM, and analyzes your program in what we call a closed world assumption. And what we're doing is we're basically looking at your program from the entry points and starting to check, so which classes are you using? Okay, I'm going to load these classes and check their static initializers. And then I'm going to see what classes these classes depend on, and then load those classes. And we iterate this process, pulling in all of the classes that your application actually needs, but none of the classes that it doesn't use. So you're not pulling in all of the Java standard library, you're not pulling in all of the classes that are in the libraries that you're using. You're really tree shaking your dependencies, and you're really ending up with a tiny binary that really encapsulates only what you need. And there, all the classes are already loaded and basically frozen into this binary. And the way we do this is, the way we freeze it into the binary is, once we've figured out all the classes and all the methods that you need, we AOT compile those Java methods, and we initialize those classes, or we start initializing those classes, and we take a snapshot of that heap and save it into a binary. And so what you end up with is a binary that has some machine code for all your Java code, and that has a snapshot of the already beginning to load application of yours. And this is where the fast startup comes from. Yes?
Sorry, what does AOT mean?
Ahead of time, I'm sorry. Yes, I should have mentioned ahead of time compiled. So what that means is when you start up your GraalVM native application, you one of the reasons you're faster is because some of the work has already been done at compile time, right? You have already initialized some of your classes. You've loaded all of those classes already. You don't need to hit like the rt.jar again to figure out which classes you need and all that stuff. This is just kind of a really, really high-level, small example again. If you have like a Hello World Scala program, you run it on the JVM. This is the kind of startup you get, and if you push this through native image, you get a native binary that doesn't have a dependency on like normal JVM on your system, and you immediately get like an order of magnitude speed up. And this is for a tiny application where you really, when you're starting the application on the JVM, you're really not spending that much time loading classes. It's just a hello world. So the order of magnitude improvement that you can expect for startup with native image in a large application is much larger. And you can see this if you went to any of the Leiden or Quarkus talks. You can see this if you look at microservices where they're using native image, and they're kind of really pushing native image also for their own products to start up much, much faster, because you're not going through all this meta stuff to figure out which classes you need and load them. And the same is true for these services in terms of memory footprint. You're easily cutting your memory footprint by a factor of 5 or more. Now, before I talked about just-in-time compilation, and now I talked a little bit about kind of mentioned AOT compilation. These two things are separate, but they go together, obviously. You could have a native image where you're just running the AOT compiled code. You could have a native image where you have the AOT compiled code and the just-in-time compiler inside also, and combinations thereof. If you have both, yes, go ahead.
Sorry, you might have been just about to cover it. Does that allow you to add additional classes?
No.
To the class spec?
No, it doesn't allow you to add additional classes, because we have this closed world assumption, and only if you have this closed world assumption can you actually get down to these small binary sizes, right? Because if you don't have that, then you're basically just pulling in all of the JDK libraries again, and what are you going to win, really? Yeah. So what I was going to say is, if you have a native binary and you still have a JIT compiler inside of it, obviously there's still going to be some warm-up difference. It starts up fast, and there's already kind of optimized code in there, AOT compiled code, but as it profiles your application, the just-in-time compiler might re-optimize some of these methods that you have inside your binary. You can improve that warm-up once again if you go through a multi-stage process and use profile-guided optimizations, which we support with native image, where you create one binary that's instrumented, and then you run some of your workloads. It will notice what kind of optimizations it should be doing, and then it will create a new binary with more optimized code and further cutting down on startup time. You can iterate these. So you can create more profiles, and then the native image can incorporate these profiles. And here, just as a kind of warm-up curve, rough idea. So with native image, you're fast from the start. You're really not warming up very much anymore. And on JDK, obviously, you need some time to warm up the code and everything until you reach kind of the same performance. This drop here at the end, kind of an artifact of this measurement, and technically there are still like a few cases where we're slightly smaller with native image, but we're working on that, and it's really nothing that's super concerning, really. One of the things that is noticeable sometimes, especially with longer running applications still right now with native image, is that the GC that we have when you create a native binary from GraalVM is not as good as the one that comes on the JVM, as some of the GCs that come with the JVM. But we're working on that also. We're creating a new GC that's going to be better and much faster and more suited to high memory workloads also. The other part where native image really shines, again, is the developer productivity. If you have command line tools, these need to start fast, warm up fast and finish fast. And here again, if you have a profile-guided, optimized native image tool, and then you run these command line tools, you're just gonna be much faster. Even for tools that start up fast and then run for a longer time, like Scala C. So Scala C is one of these tools where, like, it takes a long time usually to start it up on the JVM, and then it may continue running actually for quite a long time, where the JVM eventually will also warm up. And even there, if you're on Enterprise Edition, you still beat anything you could run on the JVM through the fastest startup and then the peak performance. So the native image and the tooling around it is ready for wide adoption, and we've seen lots of people use it already. We sorted out most of the unsupported features. It's very well documented what is unsupported and how to work around these things. For example, reflection and additional, like, dealing with resources and all of these kind of things that are more dynamic can be dealt with native image. And so really we are encouraging people to try the frameworks, to use it with their applications, and if there are any issues, report them. We are very active on GitHub and really try to really engage with the community there. Now, all of this, what I talked about, was kind of for these server workloads and desktop machines, developer machines, so kind of x86, 64. But we are also adding other backends to the native image to target other platforms, like mobile platforms or kind of store apps that are restricted in some sense or another. One of the ways we're doing this is supporting LLVM as a backend for native image. So rather than creating a machine code binary, we create an LLVM bitcode file, a binary with LLVM bitcode inside. And this has multiple advantages. One of the advantages, obviously, is that now this thing will run or can be targeted to any platform that LLVM supports. So if you have some niche platform, but LLVM supports it, this will allow you to take your Java application, or really any application in one of the languages that runs on top of GraalVM, and turn it into a binary that runs on any of these niche platforms that LLVM supports. The other advantage is that in case, for example, Apple starts requiring LLVM bitcode when you submit apps to the App Store, we got you covered also, because we're not just creating a binary that's kind of a black box. We actually create bitcode, and then you can submit that, and they will use that. So this is not. So the current state shouldn't be taken as, oh, this is the entire story. It's really an outward-looking story where you can increasingly be sure that if you're creating an application that can be turned into a native image with GraalVM, it will be easy to port it to different platforms because of these backends that we're supporting. At this time, the LLVM backend is still very new, and using it comes at a price. The GC that we have for LLVM is even more experimental than the GC we currently have in native image anyway. But as I said, we're working on GC for native image in any case. So this will be fixed sooner rather than later. The other thing is that, and the other two things are really kind of derived from the same thing, but it might not be obvious, so we put them separately here. The runtime generated code is slightly slower if you're outputting an LLVM, if you're outputting a binary that runs LLVM bitcode. And the fact that the runtime generated code is slower includes, of course, that just-in-time compiler that's part of this image, right? So if everything else runs slower, that just-in-time compiler also runs slightly slower, and that means that these LLVM-based images are slower at compilation. right now. However, we are working on all of these things and expect these will, like, if not entirely fixed, the gap will be much smaller in the future here. Now, when you write a Java application and you're using various libraries, you're not only using Java code. If you were only using Java code for everything, you're already good, you're golden. You can use native image and convert all this Java, you can have it analyze all that Java code, it will be converted into some native image, and you can run that. But to talk to the system, talk to the underlying platform, everywhere in some of these system libraries like JavaFX, there is going to be some native code that has to bind to the platform. And we partnered with the Gluon guys to create kind of Java wrappers around JavaFX and some of the libraries that you need to talk to the platforms to create Gluon Mobile, which is a kind of a set of libraries that you would need to write applications that can then be transformed via native image into binaries for other platforms like iOS, for Android, or for other store apps. And these additional libraries not only wrap the existing functionality that you would expect from kind of JavaFX libraries or whatever, they also, this work comes with the tools and the integration with Maven and Gradle to have your integration with your IDE, to have the entire process of writing your app, running it on the desktop, debugging it on the desktop, creating the native image, deploying it to the simulation targets on your desktop machine, deploying it to the real targets, the real mobile devices, all in like one nice little package. And there's also support for these additional features that some of these mobile platforms have, such as GPS sensors, orientation, and all these kind of things. Now, one of the problems that we had before was that Apple doesn't allow creating and running dynamic code on their mobile devices. So you can't actually run a just-in-time compiler. And here's where this split that we have between we can AOT compile things and we can just-in-time compile things and we can profile things comes in really handy, because while if we're interpreting everything, it's going to be slow, but if we AOT compile and profile and then compile again with these profiles and can generate already optimized code, you're going to get very, very good performance even without just-in-time compiling on the platform. And there's additional advantages, obviously, because then you suddenly, because you're not allowed to just-in-time compile anyway on that platform, you can not ship that. And you also save the CPU time on that platform to do it, which is, especially on mobile, an interesting and important thing, because you want to be saving battery on these devices, right? So you don't actually want to run, you want to do most of the optimizations on your development platform as you're developing, and while you're creating the image, you want to be able to spend the extra time there rather than on all of your end users' devices and have all of them just in time compile all the time. So this is also an advantage really over just for example, cross-compiling something to JavaScript and then having it jitted on the platform. Because then you're just pushing all of that work to all of your users' devices, and you have them run hot and them waste their batteries millions of times over again. Yeah. So I already mentioned the tooling. So Maven, Gradle plugins are available to tie all of these things together. So you can, right now it supports Java and Scala compilation, and it ties together the compilation of the code with the native image generation, linking with all the libraries that are required, and signing for the store apps and all of these things, deploying it, and we support for these tools and for this setup, we support Java 11, 12, and 13 right now for iOS. Android, my last information was that it's basically working, but there is still, it's basically working for this app that I'm going to have a screencast on in a second, but there's some issues still that prevented us from actually handing it out to everyone right now, because they would just be reporting the same issues that we already know about. So I'm just going to show, I don't have an iOS device with me, so I'm just going to show a screencast of this iOS application that's by our friends at Gluon here. And it's just a chat app. You can find it at this GitHub URL if you're interested. It's really a small application, nice and easy to understand. And it basically when you download it and check it out, you can immediately use Gradle. You can just run it. It will build it and run it, and it will run on your platform, like on your desktop computer, and kind of give you a little bit of access to these kind of platform, like mobile platform specific things, like you can change the landscape and portrait mode. And this is just, the app isn't really interesting as such, but more as a like that this thing runs across these different platforms. So it's really just a chat app that connects to some server, pushes messages there, and then other apps that connect to the same server receive it. Now, if you downloaded this, if you checked out this this GitHub URL, you can use the same thing to run. You can use Gradle native run here to run it in the iOS simulator, in the iPhone simulator here. You first have to compile it. I skipped that in the video because compiling it actually takes a few minutes. So for this app, like on my machine, was like a couple of minutes. So it's not too bad, but it's also not great because the Java compilation itself is much faster. But it's also something that will improve over time. But oh yeah, you just saw it basically just works the same on the iOS device. And if you have an actual iOS device plugged into your machine, you can also run it from using Gradle directly, push it to that device, and run it directly on that device. Just the same. So it's all nicely integrated with Graal, and you can use your normal tools as you would expect. Develop on your platform and then deploy to any other platform. Now, why would you be using this over some existing solution like React Native? One of the advantages of using React Native right now is that because it's been around longer, it has a bigger community and thus more components are available at this point. One of the advantages of running with our solution, as I already alluded to, is that we don't run some JavaScript and plus native code, right? We don't have to warm up something on the user's device. We AOT compile everything. We profile guide the optimizations before, so you're running faster from the start. And also we have, as far as we think and know, we actually have better peak performance also than if you were doing the same thing on React Native. One thing that React Native has that we don't have right now is hot code updates, because we have this process of closed world and we analyze everything and then we create a binary that we push to the device. You can't actually easily push out new code to the device. That's something that we will kind of work around, but it's something to be aware of. We think, however, that if you can develop everything and it will run the same on your desktop machine and on these different mobile platforms, that just developing locally, debugging locally, kind of is already quite a good way to get some of these benefits that you would want with hot code updates. What we're hoping to achieve with releasing this and also pushing out Android support pretty soon now is that people are going to start using Java again and other JVM-based languages, and maybe also some of the dynamic languages that we support on top of GraalVM to build mobile cross-platform applications. The React and Flutter frameworks, for example, these are open source. So you could build wrappers for the JVM for those, and then just have those be part of your application. So when you build a native image, these things are linked in, and you push them out to the devices. Also, we could use kind of leverage these JVM language communities like around Scala and Kotlin to get people interested in writing mobile applications in whatever their favorite languages are, rather than forcing them onto these specific frameworks and platforms. And the next steps for us here in this context are we're working, as I said, we're working on improving the GC and pushing out the Android support. And for deployment to mobile, I said earlier that actually compiling the native image takes a little bit of time, and when you want to kind of iterate quickly and push things out to your mobile, you actually want to try it on the mobile device quickly and iterate quickly. That can be annoying. One of the workarounds that we're looking into is during development time, not actually creating the native image, but just pushing out a bytecode interpreter to the mobile device. So during development, you don't get the peak performance, but you get this quick turnaround time of just kind of, you can quickly try something. And then if you are working on optimizing and like tweaking the performance, then you build the native image and then you check it on your mobile device. As I said, if you're interested in this, please report problems you have, or even support us, contribute on GitHub. There have been quite large open source contributions already for the work on JavaFX, for the work on tooling. There have been contributions to this LLVM backend. So we are really very actively engaging with everyone in the community who's interested in this. And I would really just like to encourage everyone who's interested in this to join us in this community and on GitHub and talk to us about it and show off these things that you might be thinking about doing or that you're doing in this space. So we can really kind of start to spawn a community that says, oh yeah, we can again use JVM-based languages for true cross-platform mobile or niche products, hardware collaboration, development. So that's the end of the talk. So just, if you're not already using GraalVM, even if you're not interested in the cross-platform parts, use it, think of the planet, save energy. But if you're interested in cross-platform development, here's another GitHub link from Gluon HQ to get started. There's some client samples in there. There's also people from Gluon here if you have specific questions about that. And just a quick reminder, you can try the Enterprise Edition and evaluate it for free. And if you decide to use it, you would get support from the actual development team, i.e. us. If you're interested in other GraalVM topics, I'm just going to leave that slide up here. This is tomorrow's set of talks that are related to GraalVM, talks and the Hacker Garden, where I'll be sitting tomorrow. So if you're interested in any of these aspects at different levels, come see us, come see these talks. And there's more talks on Thursday, but there's way too much to fit on the slide. Okay, thank you.